All right, this is linear regression without overcomplicating it because I feel like when I wanted to learn this and watch it on YouTube, um, actually understanding the main idea and going a little bit below the main idea was way harder than I feel like it needs to be. Whether you're coming from a stats perspective or a machine learning perspective, I think it's easy just to like get the main gist. Hopefully, I can bring that across in this shorter video. Okay, so the main goal, as you've probably heard already, this might not be your first time thinking about linear regression, is the idea of fitting a line to data. But what does that actually mean? Like, let's try and define the problem that linear regression solves. Like, why is that a tool in my machine learning toolbox? So the input is data, right? But like data for linear regression, like, you don't have to think that data is really just like measurements maybe that you've taken as a scientist or economics data. I don't know, something like in a table, like I have goals scored by like Messi or something, and 0, 1, 2, 2, 1, and these are like different games, and then like or maybe different seasons, and then this year are the wins in that season. So maybe this is more goals. It'd be like 10, 20, 22, 16, I don't know. And then in that season they had like 4 wins, 3 wins, 5 wins, 4 wins. Something like that. It's like very, very, very simple data. And then you want to answer the question like, if I want to predict, like, given X goals, can I predict how many wins? And the reason this problem is called fitting a line to data, let's ignore the axes, is because if you just plotted these measurements or whatever, so you had like 10 goals scored, 16, something, it would probably look like this, right? Something like that. So we plotted the data that I went out and found on Google. But then say I'm the coach and I want to know how many goals I need to make sure Messi scores for us to get some wins. Then I'll be like, okay, say I had like, maybe this is 20. So with 20 goals scored, I need to predict the amount of wins. And so the way to do that is like actually drawing a line and then seeing what my prediction is on this line with 20. And then I can also look at 25 and see what that value is. Maybe that's like 10 or something. Cool. Okay, so that's the gist of linear regression, right? You're fitting a line of data, which means you're drawing a line so that you can make predictions on the future. And you drew that line so that it fits the measurements that you've already taken. Okay, so this is just a line, and you know the line to an equation. The equation of a line is y equals mx plus b. So we're going to have to draw this line with different m's and b's until it's the best one. It's kind of like rotating it. Rotating it and drawing new ones until we get our best one. But how do we know what best is? Like, how do we know what a good choice of M and B is? And that is where we're going to get into a little more math. But the answer is not to complicated. Okay, so let's go back to our original line. So how do you know what good is? Good choice of line. So here I'm going to draw these lines here. These are called residuals, but it doesn't really matter what the vocab word is. It's just these lines, and that tells you like how far apart our line is from the actual data. And so the notation for this is y ground truth minus y hat. So this is the measured data point, so that's this, and then this is our prediction. So that would be like the point on the line. So then the difference is just the actual length here. And then as an artistic choice, you square it so it's not negative. Okay, and then to find how good the entire line is, you sum it up over your whole data set. So this looks a little complicated. It's very notation heavy. But if you walk through it slowly, it shouldn't be too complicated. You're just summing up all of the lengths of these lines and squaring them so that they're not negative. Okay, so that is how you judge how good a line is. This line will have a very different sum of squares. This is what it's called. This is like the error that we had was, it's called the total sum of squares, I believe, because you're summing up all these like squared values. So this line will have a very different sum of squares than this line because the distances to the real points are different. So how do you actually find the best M and B? We know how to evaluate good M and Bs, but now we need to know how to find them. So there are two strategies to do that. Least squares is called a closed form solution. And that means you can get the right answer off the bat every time. Gradient descent is called an iterative solution. And we're not going to cover that because that's like more down the rabbit hole of machine learning. Because least squares is basically easier. And it gives you the right answer every time. With some linear algebra. Okay, so we have our equation y equals mx plus b. That is for the line. But in order to make predictions, so in order to make a prediction, you would use this equation, right? But for every point, you're kind of doing the same thing. So we have y equals mx plus b for point 1. And then you would kind of do the same thing for point 2 and so on. So you can group these equations together into matrices like this. So you have ones, your x's, b and m, and then, oh, no. Okay, so this is just translating this to use matrices and vectors. Because if you do the matrix vector multiplication, then you get the ground truth, ideally. Okay. This is like the ideal scenario. Because typically you would just be getting like predictions like we had before. Okay, so let's move on. So this, let's call that vector x. Let's call let's call this matrix A. Let's call this vector X and this vector B. And this looks like something from linear algebra, where we want to find this value X that gets mapped to B. And so here's like a quick linear algebra trick that you just apply. So timesing by the transpose to make sure that this is symmetric. And then you multiply by the inverse. So the first time I saw this was pretty confusing. But this is like a trick that you'll just kind of like see again, and then the next time you see it, it'll make sense. And that becomes the identity matrix. Oh shit. Cool. Okie doke. And then that identity matrix goes away. Well, we don't really need to care about it. So we know X equals this. And we can calculate this because A is our data with just a column of ones. And B, maybe that's a little confusing, but B is the ground truths, which is also a part of our data. So we know all these things already. And therefore, we can just plug all these values in and calculate X, which, remember before, holds B and M, which were the things we wanted to find. So this tells you that we know that we have like a very simple calculation to actually get the best B and M values based on our data. Cool. So, I mean, that's mostly linear regression and how to find the best parameters. You can do that for as many dimensions as you want. X can be B0, B1, all the way to B100. It doesn't matter as long as your data matches that with the amount of features, and it's all good. And then that's linear regression. I guess the next question is how to do gradient descent and maybe do it for higher dimensions and also generalize linear models. But no, this was just a simple video.